Hi, this is Mrs. Huntley. We are in the supplemental materials for Module 7. It's the packet that says the real number system on the front of it. And I would like you to open, please, to page 9. It's a note page. And our EQ for this lesson is how can I tell the difference between rational and irrational numbers? So we're going to go through the lesson. And once the lesson is over, we're going to come back and add some notes onto this page. But a lot of the notes are included within the lesson. So I just wanted to get right to it, and then we'll come back and add some notes here. So page 10, we have some fill-in-the-blank notes. Rational numbers, talking about rational numbers and irrational numbers. Rational numbers are numbers that can be written as fractions or decimals. Rational numbers include both terminating and repeating decimals. So that would be the decimals that have a terminating decimals have an exact endpoint, and those repeating decimals are the ones where we put the bar over the repeating digits. Additionally, rational numbers are all perfect squares. So the square root of 25 would be a rational number. The square root of 36, any perfect square that we're taking the square root of, is a rational number. Irrational numbers, on the other hand, cannot be written in fraction form. Irrational numbers include non-terminating, non-repeating decimals, and non-perfect squares. And you might be thinking, but wait, we've been writing perfect squares, or non-perfect squares, we've been writing them as fractions. We've actually been estimating them as fractions. We've been using those little squiggly lines to say that it's approximately equal to whatever number and the fractional part of it. Talking about non-repeating, non-terminating decimals, what do you think is like the most famous, in my opinion, the most famous irrational number? And most of you were involved in some kind of a contest last year to memorize as many digits of the number as you possibly could. In my opinion, the most famous irrational number is pi, mostly because I think people don't realize that any square root of a non-perfect square is also an irrational number, because we do spend so much time figuring out its approximate equivalent. I think a lot of people think that it is a rational number when in fact it is an irrational number. All right, let's take a look at the table down here. We have a value, and they're asking us whether it's going to be rational or irrational, and then give an explanation. So we can't just pick one or the other. We have to say why. So the first one, -12. Now, -12, let's think about this. Could I write that as a fraction if I wanted to? Sure. That would make it a rational number. My reasoning, why is it rational? I can write it as a fraction if I want to. The next one, pi, kind of gave that away when I was talking about it. It is indeed irrational. Why is it irrational? Because it's a non-repeating, non-terminating decimal. 6/10. What do you think? 6/10, it looks like it's a terminating decimal to me. Terminating, again, means it just stops. And I can write terminating decimals as fractions, can't I? The next one, 7/8. It's already a fraction, guys. Don't make this harder than it has to be. When something's already a fraction, off the top of your head, you think it's already written as a fraction. Of course, it's rational, because the first thing that we talked about rational numbers are numbers that can be written as fractions or decimals. So, yep, that one would be. The next one, this one requires a little bit of explanation here. We have a really long decimal. It's the decimal point and then 1, 2, 3, 4, 5, 6. This dot, dot, dot tells us that this decimal is going to continue, and the pattern is going to continue. So it'd be 7, 8, 9, 10, and it implies that it's going to go on forever. So it is a non-terminating decimal. It's also not repeating, because our numbers are there's a pattern of course, but it's not a repeating pattern. So that one is irrational, because it is a non-terminating, non-repeating decimal. What I'd like you to do is pause the video and fill out the next 4 and tell me whether they're rational or irrational and why you believe that, and then come back and check your work. So go ahead and pause it and come back and check your work as soon as you got them filled out. Okay, so point 33 repeating, it is rational. Why? Because it's a repeating decimal. And we learned in the last lesson, I can write a repeating decimal as a fraction. The square root of 20 is irrational because it's not a perfect square. Negative 1.75 is rational because it's a terminating decimal, and I can write it as a fraction. The negative square root of 121 is rational because the square root of 121 is a perfect square. Hopefully that wasn't too challenging for you and you kind of have got this and you're figuring out the categories. If this is something that's particularly challenging for you, what I'd like you to do is just kind of focus in on what an irrational number is, and then everything else is a rational number. So if it's a non-terminating, non-repeating decimal, or if it's a non-perfect square, you know it's going to be irrational. Everything else is rational. Let's move on to the next page. And it says, practice identifying rational and irrational numbers with the questions below. Number 1, Joseph wants to find the side length of a square that has an area of 150 feet. Should his answer be rational or irrational, and why? Okay, so let's think about this for a second. They're not asking us to find the side length, but they're asking us to figure out how we would if we were going to, and whether that answer would be rational or irrational. So let's think about squares. Our squares always have side lengths that are the same. That's what makes them a square. Now, a lot of times we show that as an S, but my S's tend to look like 5s, so I'm going to call them X. To find the area of this square, I would multiply X times X. So I'd have X times X, which I could write as X squared, right? And I know the area is going to be 150 feet. So to solve this, I would take the square root of both sides of it, and now I've got the square root of 150. Is the square root of 150 going to be rational or irrational? Joseph's answer would be irrational because 150 is not a perfect square. Now let's be clear. 150, the number 150, is absolutely rational, but the square root of 150 is irrational because the 150 is not a perfect square. Hopefully that's clear. Number 2, which value from the following list of numbers is not a rational number? So we're looking for not a rational number. So the first one, 8.224, that's a terminating decimal. Terminating decimals are rational. 5/9, that's already a fraction. We know all fractions are going to be rational. Square root of 25. 25 is a perfect square, so that one's going to be rational. 0.321 repeating. Repeating decimals are rational. Square root of 30. Square root of 30 is the one that does not belong with the others because the square root of 30, or 30, is not a perfect square. Now, I know it doesn't ask us for a reason as far as why, but I want you to get into the habit of always giving a reason, at least in your mind. So if you're picking one and you're saying, this is my irrational number, just say in your head, why is it irrational? Well, actually, I want you to write it down. So Brad converted 5/11ths to a decimal, and his answer, or his result, was a repeating decimal. Does this mean that the value is rational or irrational? Explain your answer. So let's think about it for a minute. We said repeating decimals were rational, right? Additionally, we learned in our last lesson that we can convert a repeating decimal into a fraction. Additionally, this is already a fraction. So if we're converting a rational number into a different form, it's going to be a rational number. We didn't change our number, we just converted how we were presenting it. So it would be a rational answer. Number 4, state whether the given values are rational or irrational. This is very similar to some of the problems that were on our other page. So what I would like you to do is pause the video, go ahead and determine whether you think each of these 3 different representations of decimals are going to be rational or irrational. Remember, this ... on part B, means that whatever pattern is there is going to continue, and it implies that it continues forever. So again, quick pause, and then come back to check your work. Okay, part A is a terminating decimal. We know terminating decimals are rational. Part B, non-repeating, non-terminating decimal, which means it's irrational. And part C, that little bar over the 7 means it's a repeating decimal, and we know repeating decimals are rational. Okay, number 5. These look a little bit different than things that we've looked at thus far. I don't know that we've talked about like terms in terms of radicals, but we have talked about like terms when we're combining like terms in a equation. And we said like terms have to have the same variable raised to the same power. When we're talking about like terms with radicals, like terms have to have the same radical with the same number under the radical sign. So 6 and 30 cannot be combined together because they are not like terms. So the way I would say this for part A is 6 plus the square root of 30. Now the square root of 30 is not a perfect square. So this one, part A, is going to be irrational because 30 is not a perfect square. Part B, the 6 and the 30 are both under the radical sign. So I would say this, the way I would say this problem is the square root of 6 plus 30. 6 plus 30, because they're both under the radical, I can add them together. That would be the square root of 36, which is a perfect square. So it's rational because 36 is a perfect square. Part C, you might be thinking it's the same as part B, but it's not. So we've got the square root of 6 plus the square root of 30. Again, I can only add these guys together if they're the same, if whatever is under the radical sign is the same. So this one is non-perfect squares because they are irrational. Okay, number 6, give an example of an irrational number that is greater than 10. So if you're racking your brain right now and you're like, oh, how could I do that? Let's take a look at what irrational numbers are again. Irrational numbers cannot be written in fraction form. Irrational numbers include non-terminating, non-repeating decimals and non-perfect squares. So we want our value to be greater than 10. So let's think. How could I get a value that's greater than 10 that would be maybe a non-perfect square? So the square root of 100 is 10. So the square root of any number that is greater than 100 would give me a value that is greater than 10, but it would be irrational as long as what I'm putting under the radical sign is not a perfect square. So I'm going to say 101. Is that the only possible answer? No, of course not. It could be any number under that radical that's greater than 100 and not a perfect square. Okay, so I would like you to take the next few minutes and summarize today's lesson. I'm going to flip back really quick to our note page and see what notes I had come up with. Okay, rational numbers, our whole numbers, positive and negative. We're actually going to be categorizing our whole numbers in another couple lessons, but if you want to think about it as whole numbers that are positive and negative, fractions and decimals, terminating and repeating, and all perfect squares. Irrational numbers, what are they? Non-terminating, non-repeating decimals, and any non-perfect square, taking the square root of any non-perfect square. Yeah, I guess I should say, and taking the square root and the square root. Any non-perfect square, because just because it's a non-perfect square doesn't make it irrational as long as it's not under the radical. I hope that it was clear in the lesson. So look, I'm under 15 minutes again, guys, so I'm keeping my end of the bargain. I hope if you have any questions, you bring them to me, and don't forget to do the summary, and I will see you tomorrow. Have a good night.